Hey, so this is Joe, and this is the fifth and final part of the fifth chapter of Stewart's calculus, and we're going to be talking about finding the average value of a function and the mean value theorem is applied to integrals, and they're both pretty closely related. So, I'm not going to go through the entire numerical proof as usual that's in your book, but I'm going to kind of give you the gist of it. So, and we've been doing this for a long time, especially if you're watching this video when you're in calculus, but when you find the average of a set of numbers, what you do is you add all those numbers up, and then you divide by the number of numbers there. However, if you're trying to find the average value of a function, you've got many values in that function. I mean, infinite many if you keep subdividing, and you have you're not going to be able to enumerate all those values exactly without describing them as a function, and you're not really going to be able to count how many numbers there are in there. So how do we go about finding the average value of a function? Well, we can describe the number of numbers in there. So let's say we've got a function y. We want to find the average of that set. We add up all the y's. So y1, all the y values described by that function, and for the n, we can write that as whatever the interval on that function that we're trying to average is. So b minus a, let's say that the interval is ab, just for clarity's sake. I'll put that up there. And so that's the interval divided by the number of subdivisions we're using. So let's say this is the function y, if you don't understand what subdivisions means. So this is the function y, and we have a, and we have b right there. If we take subintervals at which we find different values, so we have, for example, y1's right there, y2's right there, y3's right there. These are all equally spaced. They're all equally spaced by a distance of delta x. So this fraction right here will describe the number of y's that we're taking and we're averaging. But what if we make, and this is the theme in calculus, what if we make delta x really small? In fact, what if we use our series limit and limit talk and make it into a dx and flip this whole fraction up? Well, then we'll get an integral that looks like this. The integral between a and b of the function y times dx, which comes from that delta x when we flip it up, and then put this whole integral here over b minus a. That there is the equation for the average value of a function. And let's go over and look at a graph and kind of play around with this so we can get a better intuitive understanding for it. So here we've got the function f of x equals x to the third. And let's say we want to find the average value of this function between 0 and 1, which is right here. Let's say we want to find the average value of that function. Well, let's just start off by using the equation that we found earlier. So we'll get the integral from 0 to 1 of x to the third dx over 1 minus 0, so over 1. Well, let's see what that means graphically. So this integral right here is the area. It's this area right here. And this dimension is the 1. So that's the dimension there. And then the f average is going to be some value of y. We don't know exactly what it's going to be, but it's some value of y. Well, we have two linear components, and we're multiplying them together to get an area. Well, generally, when we multiply two linear components together, we get a square or rectangular area. However, of course, this area isn't square or rectangular. So that means that the average value of the function multiplied by the interval, the interval over which you're integrating, those two values will give you a rectangular region, the area of which is equal to the area under the curve you're trying to find the average value of. And that's pretty neat. And that'll hopefully help you in problems to come, and also it's a good way of checking yourself to make sure you're doing this right. So let's actually go and solve this. So we bring the 1 over, I'll just write that 1 out so it becomes clear. We got f average. We integrate this, we get x to the 4th over 4 between 1 and 0. We plug the 1 in, that's 1/4. And so we bring the 1 over, and the average value is 1/4. So that is the average value of the function between 0 and 1. And we also now know that this rectangle here is equal to the area under the curve. So that's a kind of good way to remember how this function works if you don't remember it using the kind of average slash limit approach that we did on the other screen. So that's how the average value of a function works. Now let's go back and see how this relates to the mean value theorem. Alright, so I'm going to kind of work backwards when we talk about the mean value theorem from the perspective of an integral, and work back from the conclusion that your book gives you. So we've got, this is the average value of your function, and your book and the mean value theorem tells us that there is some value of f at c, where c is between a and b, so it's in that interval, where there's a function, f of c is equal to the average value of the function, which is equal to this expression right here. So that means that the function passes through its average value on the interval. And that kind of makes sense because the average is generally sort of in the middle of all of the values in a given set, and so it makes sense that the function would have to pass through that over the set you're integrating, kind of intuitively. However, let's look at this on a graph and see how this makes sense. Alright, so remember when we have our function x to the x cubed, we got that its average value is 1/4. So here's 1/4 right here. And 1/4 is a value of f on the graph of f between 0 and 1. And so that means that there's got to be a corresponding x value that when plugged into the function will yield the average function value over this interval. And that value is c. We can calculate it, but it doesn't really matter. It exists. We can see it on the graph. And when you plug c into f, that's going to give us the average value. And so that's what the mean value theorem integral style tells us. And it tells us a very similar thing to the differential version, which I'm going to show in just a few seconds, which also tells us that given a certain interval, if we take the average slope over that interval, there's going to be a derivative value at c that the function passes through. So it's kind of the same idea. You get a broad interval, you do something to it, and you know that there's got to be a value somewhere that satisfies a certain condition. That's really vague, but on the next screen, what I'm going to do is, if you still don't believe me, you say, hey, you just kind of pulled that formula out of nowhere, prove that it's actually the mean value theorem. I'm going to show you how, actually using a problem in your book, show you how the differential and the integral mean value theorems kind of lead to the same place. Problem number 3 at the end of the section in your book says, given this equation right here, very general integral, oh, that b is supposed to be an x, excuse me, given this, and given the differential mean value theorem, derive the integral mean value theorem that we just found right here. So, first off, if you don't remember, I'm going to remind you of the differential mean value theorem. Alright, so the differential style of the mean value theorem states that if you've got a function f, its derivative at c is equal to the average slope of the function between two values a and b. So remember, this is like the average slope formula, this is the derivative formula, so the instantaneous slope at c is equal to the average slope between b and a. And so how are we going to get to the integral version of the mean value theorem from here using this? Well, let's start by making this first function look like that one. So draw this over here. So what we're first going to need to do is take the derivative of big F at c. So take the derivative of big F at c. So let's just think of this as one function. Let's ignore this for a second. So if we're going to apply the differential mean value theorem to this, all we'd get is big F, its derivative at c would be equal to big F at sum b minus big F at sum a over b minus a. And that's the differential mean value theorem. However, remember, this is an integral, and the derivative is the inverse operation of the integral, and since this is a general integral with in terms of x right here, when we take the derivative at c, we're plugging in a c for the x, but then we're differentiating, and so that c would carry through into this function right here, and that integral would really just go away, and you'd get a little f of c, like that. And then this big F at b, well, you plug in a b for the integral right there, you get a integral from a to b of f t dt minus the integral from a to a and f of t dt over b minus a. Now, okay, so this is weird. The integral from a to a, that means that there's no change in the t value right here. So that means that integral is 0 because there's no change. You're not adding anything up because you've got the same limits on both ends of the integrand. So that expression right there is going to be equal to 0. So we've got f of c is equal to the integral between a and b of f of t dt minus 0 over b minus a. Lo and behold, that is the integral style of the mean value theorem. So that shows that really the mean value theorem is one thing that can be thought of either in terms of the integral or in terms of the derivative. And one has repercussions for knowing things about a function's slope, the other about knowing things about a function's area and average value. So that's it for chapter 5. I hope maybe you learned something or cleared up some problems for you. Stay tuned for chapter 6. We're just going deeper into calculus.